Greetings, everyone. It is Professor Jamison-Hooks again, sharing with you a video that we will look at in terms of averaging. Averaging is normally done on FPGAs in real time, on any real-time hardware to increase your signal to noise ratio. It's sort of like if you're taking a picture of an object and you're looking at it over and over and over again for a period of time, you stack those images on top of each other and you average it. And that way you can increase your signal to noise ratio and and that's always good. But at the same time, there's a limitation to how much averaging you can really do on hardware because of resources. And for that reason, normally there is post-processing averaging that occurs. And today is what I will cover. Um, and as an exploration topic, I would encourage persons who want to dive a little deeper into learning how to put together an averaging algorithm in Simulink to start exploring that topic. And I will probably give you some hints and tricks in an upcoming video. But for now, we're looking at everything in a that I'm covering in this blue box that can go onto an FPGA. I'm in the MATLAB Simulink environment, so as usual, those who have been working with me know that you can create your own sinusoidal wave inside of your FPGA using an HDL numerically controlled oscillator block from MATLAB Simulink. You can take your FFT, your fast Fourier transform, and you can incorporate a Cordic block, which is this magnitude block right here that could take the magnitude of your FFT. And here I'm showing that imagine that I'm on a spacecraft and I have my data packets and I'm sending them off. So I'm sending off my data to the spacecraft to store the data, to downlink it. And so what I'm going to do with this data is come into my MATLAB script and perform post-processing averaging, which will be occurring down here. And so I'm going to walk you through that process. The first thing I need to do, again, you have worked with the NCO several times. You know that this script is part of the package that MATLAB Simulink includes. And I am using an FFT size of 512. I am using a sampling frequency of 60 megahertz. And my incoming signal, my desired output frequency is going to be 15 megahertz. I've just copied old code because we've done this several times, so you should know how to do this. And so what I'm doing is making sure that I'm sending all these parameters into my Simulink model so that it has everything it needs. So my enable block here has my sampling frequency. My NCO block has all the parameters that I've just created. My FFT block, I parameterize the length here, and so it's 512, just like it is in my MATLAB code. And then I have my magnitude block. But here to my two workspace block. So this is what's neat about Simulink is that I can do post-processing in the MATLAB environment, which sometimes is much easier by using the two workspace. And there's also a from workspace block. And here it's important that you save the format as an array and I make it a 2D array. This is really important. Everything else, you can leave it in its default format, but make sure you do that. Okay. And make sure you need your valid signal. You always need to know what is my valid data. You don't want to start looking at data until it's valid. All right. So again, array 2D, everything else you can keep as default. Okay. So I find with my sampling rate, I don't want to run this really long. I don't want to get too much data because I'm sampling at a rate of 60 megahertz. I don't need to run this design for like 1 second. I don't want to run it at 10 seconds. I want to run it at a fraction of that time. Otherwise, I'll be waiting because this is running in real time, and real time is much faster. And you're getting more samples. So you don't need to run it as long. And I don't know if that made sense, but I think you can figure out what I'm trying to say. All right. So here I'm verifying that I'm getting the tone that I am expecting. And here it's important to note that I have taken the FFT. So here I'm not looking to do a spectrum analyzer. I'm looking at seeing my frequency tones. And so I have a time scope that I'm looking at because my data is coming out in time. The FFT has already been taken. So what I get here is what I would have in terms of my samples marching out of my FPGA in time steps, according to whatever clock my FPGA has. So here, I haven't done an FFT. So, of course, my spectrum analyzer is doing an FFT on my time domain incoming signal to verify that I have the correct frequency. Okay. So I run this because I ran my MATLAB script and all my parameters are set and I don't need to wait a long time. All right. I got a lot of data with just running it for this amount of time. All right. Got a lot of data because that's in seconds. So here I verified that I'm at 15 megahertz, and that's my NCO verification. And my time verification is telling me that I should have two sets of tones, right? These are my two sets. Oh, sorry. That's not it. These are my two sets of tones, and they are marching out of my FPGA. All right, so what do I do with all of those tones? Those are the sets of tones that I want to average, right? So therefore, I use these parameters, I come into my MATLAB script, I go down here, and first I need to determine, oops, okay, let's do this. All right. I need to first determine what is my valid data? Where do I want to start looking at this data? So the first thing that I do is let me increase this. Okay. I find out when my valid data, and this is the name of the valid signal from my MATLAB script, my MATLAB Simulink script. This is the name of that data. See? Sci info underscore valid. But let me go back a step in case for those who may forget. Okay, first, whenever you run your Simulink model, you have these two workspace elements. You should double click on out and you should verify that your data is here. Like you have your information, you have your sci info and you have your sci info underscore valid. So you have your data right here. All right. So that's going to be in this out parameter. And so remember that this is not just called sci info underscore valid, it's called out dot sci info underscore valid. And so you're accessing that from that two workspace element array from here. So you use the find command to determine when is it equal to 1. Now, I only want data when K is 1. All right. So I don't want it when it's 0. So what I do here is I name a new parameter because I don't want to carry around this name anymore. I name a new parameter called FFT data. Many times it's not, I would call it MAG data, but it's FFT data. That's fine. And that will be called out dot. And then I would take a subset of the data because all the data isn't valid. It's only valid from k equals 1 to the end of the data. Because I ran it for an arbitrary amount, I got a lot of data. I don't know how much it is. I don't know how many sets of tones there are, but I'm just going to grab all the valid data and I'm going to name it a new parameter. That's all I'm doing here. And you want to get used to understanding how to do this because you want, as a science hardware engineering platform specialist, you're moving from a traditional FPGA designer to basically defining your measurement and understanding how to post process your measurement. Okay. And that means that you need to understand your data. You need to understand how to unpack it, how to read it, how to verify it for yourself, not to just take it default to the scientist to tell you what you just did works. You need to determine what you did works. You're merging disciplines. You're no longer siloed into a traditional FPGA or engineering role. You are a science hardware platform specialist. Now, based on the size of your FFT, you want to start controlling the lengths. So you have this A parameter, which is A equals 1 to your FFT length, and you want to determine, you want to plot one part of your data. So let's do here. Let's go and run this part. And you're just plotting one set of your data. You're plotting the complete FFT length of just your FFT data of 1 to your FFT length. So you've already gotten your valid data. Now you are looking at that valid data and you're saying, I only want one set of those tones. I don't want to see all of those tones. So let me see what I get here. Let me run this code. Yeah. And see, you get one set and it's in a specific bin. And this bin corresponds to the frequency that you have sent, the way you scale to determine if bin 129 has your correct frequency is the equation for that. So write it down. Your F0 equals your bin number, which is 129, times Fs over your FFT length. So once you determine, does 15 megahertz, does that occur at bin 129? The equation is your frequency F equals your bin location times Fs over FFT. And so that's how you determine if bin 129 is the correct bin for your frequency. And this bin 385 is the image tone. That is your image tone. All right. So now we go here and we want to determine how much do we want to average? How many spectral averages do we want? Well, we need to see what is the maximum number of sets of tones we have in our signal, because we can run this arbitrary amounts. So we don't know how many sets we have. So we get the length of our FFT data, right? So we want to get the full length of this and we want to divide it into FFT chunks. And we need to get the floor of this. We need to get the minimum of how many sets of FFTs do I have in my data. You want to get this length. And then you want to say, okay, now that I got this length, I want to see how many spectral averages that I can take on this data. And I'm just looking here, and I don't think I have one important parameter. Yeah, no, I do have it. So I have the number of spectral averages that I can take. And so that's what I do here. I go 1 to the number of spectral averages times the FFT length. All right. So this might require some thinking. So think. And the next thing that I do is I reshape my data here. I reshape this data so that I have my columns of FFT, no, my columns of the spectral averages that I can take. And the rows are my FFT. All right, we're going to look at this because looking at it makes things a lot easier to kind of see. So here I'm arranging my data and I'm looking at, oh, I have enough data to do 56 spectral averaging. So now let me look at my data here. Yeah, looking here. And remember, it is valid, but zeros are valid, are valid, okay? Are valid numbers. And remember, we peak at in bin 129. So it's important that when you see zeros, you don't automatically start thinking, oh, this isn't valid data. No, 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 it is valid data. Zero is a valid number or a valid data sample. All right. And here I'm saying that I can take 56 averages, right? And the length of each column is my FFT length. The length of the column, the rows, number of rows of each column is my FFT length. So what am I saying here? I'm saying that I can average, that means I can add, I'm going to add all of these columns into one. Okay. So now, what do I use here? I use the sum command. And the 2 corresponds to the fact that I'm summing along my columns. All right. So I'm going to take off this hold and we're going to see what we get. All right. And let's look here. And what's important about here is during the arrangement of your data, you are making sure that you have arranged your data correctly so that everything adds on top of each other. If this is one tone, this represents one FFT data set. That's just one. This is your data for one particular like capture of data, right? Now, if I'm going to add successive sets of FFTs together, then I need to make sure that they are aligned correctly. That's important. That bin 129 is not shifted when I'm averaging the next set of FFTs by 1. That means that it won't look the same. It should look the same and stack up on top of each other perfectly. But if you notice on your y-axis, adding successive tones together increases your values for your y-axis. And this tells you that you are averaging correctly. And this is what you want to verify before you implement your algorithms inside of the Simulink model. That's very, very, very important because even when you implement the averaging in Simulink, you are still taking the data from that Simulink, and you can imagine that there is still post-processing averaging happening even once the data hits the ground. All right. So you're averaging, 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 but it's important to do the real-time averaging on the FPGA. All right. So that is your stretch goal, is to take what I have described here and implement it in your here. You should have a number of blocks and block RAM to do a Simulink model of the spectral averaging that's described here, right? And at this point, you'll understand that your data is marching uh, out of these blocks, one sample at a time. And I think this is why it's so important for me to give this kind of exercise to students, because they sometimes think that data just appears all at once. It doesn't appear this way. It appears in successively over time. So we get data, 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 one clock cycle at a time. And that is exactly how you need to operate on this data when you are building real-time systems. There's things such as latency. So all of this latency occurs, and this is why we don't have valid data until we add up all the latencies plus one, then I have valid data. And then I have data going as long as my system is running. And I need to be able to average it. Okay. So, averaging really gets engineers and FPGA designers and scientists out into the mindset of real-time operations and out of the mindset of immediacy. Like, I'm going to get my data as soon as I press run. It doesn't happen that way. And the subsequent processing of your data, the averaging of your data happens on a sample at a time. And so this is your stretch exploration project, is to take what you're learning and what you're seeing and what you're understanding and start to implement it in, in a Simulink model that can be deployed on hardware. And for that, I can tell you that you will need the following type of blocks. You'll need a RAM. Let's see, true dual film. Simple. I think a simple RAM. Is it called that? I forgot. Okay, let's start with the dual port. Simple dual port RAM. All right, we gotta wait. This thing is, yeah. So you need a simple dual port RAM. You'll need a HDL counter. You'll need two of these. Okay. You'll need I'm giving you a hint because I want you to work on it. You'll need a fast counter and you'll need a spectral averager counter. Oops. Cancel. Okay. I'm doing this on the fly and I've never been good at freestyling. So spectral averaging counter. And then you need to kind of imagine that you'll need a log 2 of FFT length kind of depth for your RAM, right? Your block RAM. Because what you're doing is you're having enough block RAM, enough address space in order to fill this block RAM with one FFT length. So this is an FFT length block RAM. And you're sitting it here and you're saying, I'm just going to keep averaging until I reach the number of spectral averagers. But in the beginning, I need to count up to my, oops, again, my fast counter needs to count to log 2 of FFT. Spectral averaging is whatever number that you are averaging. You could be averaging 1,000 um, FFTs, okay? So, and then you'll need, of course, a sum block, right? All right. These are your building blocks. Oh, the other thing you'll need is no, that's not it, a switch. You'll need a switch. Okay. These are your magic buttons here to create an averager. So the main thing is before I go to Simulink, I usually go on pen and paper and think about what am I doing? I am counting up, like when I have a valid signal, I'm not I'm not filling up my memory space until this thing is valid. And then I start filling up my memory space with 1 to FFT size. And then this output comes around and feeds into this guy, right? And then I determine when I am like when and how I'm going to sum. All right. So the first thing you need to do is fill up your buffer. And when you're filling up your buffer, one of these plus signs will be 0 for a period of time. Hint, hint, 512 clock cycles. And then you're filling up your data because your real-time data is coming from here. And then when this is no longer 0, you're adding your spectrum on top of each other. But everything needs to be timed. And these counters give you your addresses, and this spectral averager kind of feeds and tells you how many averages you're doing and when to read out your data. So this switch is kind of saying, okay, I'm going to read out my data now. All right. So I've given you like some good hints right now. I I really encourage you to go for it. Go to the exploration portion of this project. Go beyond what is being asked. Okay, but another necessary component of this for my students that are in my class right now is that you need to harvest the FFT and the magnitude block and attach it to your Simulink digital down converter. This is what needs to happen. All right. You have to attach it to your digital down converter, and you're going to have to append your down sampler at the end, and you're going to have to do your post processing just like we had done. So I've demonstrated how the post processing algorithm occurs. Then I've demonstrated how one can create a real-time averager inside of the FPGA. And then the other necessary component is that you append the FFT and magnitude block to your digital down converter block in your Simulink model. And remember, you're going to need on the output of this guy, you're going to need your down sampler block, right? Because that's part of your digital down converter. And then you take your data into Workspace and you go into MATLAB and you verify that your data is showing up in the right places. All right. So this is it for now. I've enjoyed sharing all of these programs with you, projects with you, making design fun, making it understandable, making it so that you become that science hardware engineering platform specialist that you are, and moving our disciplines into true multidisciplinary products of research and fun. All right. So have a great rest of your day. See you next time.